Okay, got it. Shall we start? All right.
It's on record.
It's very nice to have Tomas Andrade today here. I think most of you already met him. He's been here the whole week. Tomas has worked in a variety of things. I know him from his work in holography. He has done very important things, but now he's also working in gravity waves. He will have a talk on that on Tuesday. Very nice. And today he's going to talk to us about black hole collisions and violations of the weak cosmic censorship.
Thank you so much, Daniel, and thank you all for being here. It's a real pleasure to be in Madrid. Before the pandemic in February 2019, the last trip that I made outside of Catalonia was here. And now I'm in the pre-pandemic. I don't think we're in the post-pandemic. But yeah, you can probably come up with some cheap metaphor for closing cycles. But yeah, it's great to be here and being able to see you all in person. So yeah, maybe this is some sort of pivotal project for me. As Daniel mentioned, I used to work a lot on holography, and now I'm working on gravitational waves. I'm part of the Virgo collaboration. And I feel like this project was sort of the transition between the two. Something in between gravitational waves and high energy physics. And of course, I continue to work in holography, and now I'm doing work in gravitational waves. And this is somewhere in the middle, I feel. It was a sort of pivotal moment for me about 3 years ago. I also quit smoking at the time of starting this project. So yeah, it was like a big deal for me. So it was great. Okay, so I'm going to acknowledge my badges. I'm part of the University of Barcelona, also the Virgo collaboration, and I'm a developer for the GR Chombo code. The simulations that I will show you during the talk were made using this open source software. Okay, so my take-home message is can be summarized in 2 videos. So this first video here that I will play in a second, this is a movie made with a high frequency camera of a fluid that is falling because of gravity, but unrelated to gravity, this fluid is unstable towards the modulation because it's very thin, and we know that there's an instability called the Rayleigh-Plateau instability that causes this fluid to break apart. So it's going to start raining tomorrow. It's going to rain the entire weekend, and you will experience that you're not going to be rained on by tubes. You're going to be rained on by droplets, and this instability is the cause of that. Right. So this is an experiment that was filmed. This is a simulation that we did, and we observe a very similar phenomenon here. So instead of having a fluid that breaks up, we will see a horizon that will break up after the encounter of 2 black holes in dimension 6 and higher. So here we go. Let's see if it works. This is the fluid. You see that it develops this modulation, and ultimately this modulation causes the fluid to break up. So there's a pinching off there of the tube of fluid. This is something that's been well known for many years. What hasn't been that well known for many years is that horizons can do similar things. And in this case, we managed to construct this circumstance where 2 black holes that merge can undergo a similar cascade. So we have 2 black holes that collide, they fuse, and instead of settling down to a spherical black hole the way it happens in 4 dimensions, the horizon continues to grow. It becomes very thin, and because it's very thin, something similar to this will also happen, where you start seeing this bead formation and an instability cascade. One.
That's a 2-dimensional projection.
Yes.
What happens in the transverse dimension for that transverse dimension?
Yeah, not a lot. We're assuming that there's a symmetry in the other directions. Most of the interesting dynamics happen here.
So it gives every single circle in that image.
It's the 4D sphere. Yeah.
Okay.
Yeah. Thanks. We're using the cartoon method. I don't know if you're familiar with that trick in numerical geo. Okay, so we have a simulation, and in principle we can stop here. We've achieved what we wanted to show, but it's interesting to try to provide some intuition for why this should happen, why we would expect this to be the case, and explore some of the physical consequences of this phenomenon. So just to talk to your system one, we're gonna give a very, very cartoonish picture of this. We start with empty space. There's no cosmological constant. There's nothing, and we have two black holes, and these two black holes will merge. They will form an elongated horizon, and we know that elongated horizons don't want to stay put. They want to break up because of the Gregory-Laflamme instability, and ultimately, this Gregory-Laflamme instability will cause these two black holes that were merged to continue going their own ways. So this is the cartoon version of the picture before. Yes.
I'm not seeing the animations in the group.
Ah. Oh, that's unfortunate.
Maybe you can unshare again. No, they are static.
Okay, I can try that. What about now? No, I don't see it here. But you're right. On my screen, they're not animating. Yeah, I don't know why that's the case.
So if you remove the share screen, let's see. And share the screen.
Yep. Stop share.
Okay, now try again. Share the screen. Yeah.
Yeah, no, it's not showing me the control bar. Okay.
You should launch the slideshow in a window and share that window. That's probably what's going on.
Yeah, instead of sharing the screen, share the keynote.
Okay, like that's what I'm trying to do now.
Oh, that's something I wouldn't be surprised.
How about now?
Yeah, now it works.
That works? Okay, great. Yeah, thanks for letting me know. Okay. Good. So now in words, what we've observed is that if you have a black hole collision that forms a long horizon, this long horizon can pinch off due to the Gregory-Laflamme instability. And this constitutes a violation of cosmic censorship. We will say a lot more about this, but the idea is that singularities were conjectured to remain inside black hole horizons by Penrose. And this example here is one of the many examples that we now know where this conjecture is violated. So the moment of pinching off is a moment where arbitrarily high curvatures are accessible to outside observers like us. And this conjecture is violated in this setting. Exactly, yes. It does happen in some circumstances, not precisely this one. Sorry, what's the
role of the other dimension here?
Well, astrophysically, I don't think there's a direct connection. But at least for me, the motivation of doing this work is that by understanding the counterexamples, we can understand maybe how to formulate the conjecture in a way that it can be proven as a theorem. Yes.
And you might have a different strength of gravity.
Sure.
So that might be the reason why you get
Yeah. That's intuitively, I think it's the right answer, but it still remains an open question how to reformulate this in a way that in 4 dimensions with generic initial data, this doesn't happen. There are some 4D counterexamples, but that require fine-tuning of the initial data. So that's something that we also need to rule out in order for this to be a proper theorem. Thanks. So yeah, as Juan was saying, we need higher dimensions for this. In particular, this effect, we've observed it to occur in dimension 6 and higher. And it's also important to mention that this is like many other examples. The first one of them historically was a black string studied by Lehner and Pretorius about 10 years ago. But in that case, and in all these already known counterexamples, you start with a configuration that is unstable, that you perturb it, and then you form a singularity. In our case, the black holes that we're conducting are absolutely stable. So in principle, you shouldn't expect a singularity to emerge out of dynamical evolution. But we've seen that it actually happens, and I think it's fair to say that this is a truly generic effect, since the initial condition you started with is stable. And I think this is a community effort. So there's been many counterexamples. We're building up this whole family of configurations that break this conjecture. This is a plaza a couple of blocks away from where I live. So speaking of team efforts, I'd like to acknowledge my collaborators, Pau Figueras and Ulrich Verhake. This work, we wrote this paper, the three of us. All I'm going to present here is based basically on this paper. It was previously inspired by these two papers on the archive, done in collaboration with Roberto Enfaran, David Licht, and Raymond Luna. We were, in these papers, we formulated an effective theory where we could see this phenomenon in an infinite number of dimensions. I'll tell you a little bit more about that. And our goal was to motivate some people to go and create this infinite number of dimensions, and I decided to become myself involved in this project. And a few years later, we were able to do it. So here's the outline. I will say a few words about the weak cosmic censorship conjecture to begin with. I will also show you what's the basic mechanism to break it. I will say a few words about the effective theory that we use to guide our intuition. And finally, I will show you the results of our simulation and numerical relativity and finite number of dimensions, but higher than 4. So what is the weak cosmic censorship conjecture? So this was formulated by Penrose in the late 60s. And the way that I like to start talking about this is by remembering the words of the physicist and writer Ernesto Sábato, as some of you might know. He worked on relativity himself, but then he became a writer. So in an interview that I really like, someone asked him, well, what is general relativity? And he gives this answer. He says that the general relativity is like a cathedral of theorems. So you have, the axioms of the real numbers, on top of that calculus, on top of that have differential geometry, and you have this beautiful structure that everything has to fit together for this beautiful structure to emerge. And my only commentary to this sentence is that this cathedral is under construction, that is missing maybe a few blocks that need to find a place, and the weak cosmic censorship conjecture is one of the missing bits that are still trying to find its place within this beautiful structure. And what is the physical content? Essentially, that singularities always remain inside black holes. So Penrose was really worried about singularities because him and Hawking have proven a theorem that says that singularities are a truly generic thing in relativity. And he said, well, we cannot possibly live in a universe that don't allow us to predict anything. That would be the case if the singularities are everywhere unprotected from us. So he conjectured that they should always remain inside black holes. And yes, I said it's a conjecture, but it's very reasonable to expect that in our universe, this conjecture is actually true. We're trying to flesh out exactly how to prove it. So yeah, connected to that idea, Penrose was awarded the Nobel Prize in Physics for, I think, basically the sentence is that he was able to provide evidence that black holes are a robust prediction of general relativity. So you don't have to try super hard to make a black hole, as Einstein and many other people believed in the early days that, well, this was just a mathematical artifact, and you really have to fine-tune things. You're assuming spherical symmetry and so on and so forth. But if you let gravity do what it wants to do, you will never see this. And it turns out that this is not the case. So black holes are there in the universe. We've seen many of them by now. And Penrose was awarded this prize by providing the sort of mathematical formalism that allows you to understand that a little bit better. So what is this black hole syllogism? So syllogism is a way of reasoning that the Greeks like a lot. You start with two basic premises that allow you to conclude a third. For example, all humans are mortal, Aristotle is human, hence Aristotle must be mortal. That's more or less the idea. And here the reasoning is also you can split it in the same way. So what is the first leg of the syllogism? That singularities are robust. This is a theorem proven by Hawking and Penrose in 1965. So this is the first part of the syllogism. The second part of the syllogism is a conjecture. This is the weak cosmic censorship conjecture that says that black holes are always, that singularities are always censored by black holes. If you put these two things together, you conclude that black holes are themselves a robust prediction, that they must be everywhere simply because they're predicting something that always occurs. But well, there's a little bit uncomfortable that this is a conjecture. It's not, doesn't stand on the same ground as this theorem. But so far, we have no counterexamples of astrophysical relevance. What do I mean by this? That in 3+1 dimensions with generic initial data, we haven't been able to construct a counterexample of the weak cosmic censorship. Good. So there are essentially two kinds of counterexamples, critical collapse and what I call here death by fragmentation. Critical collapse was the first one historically that appeared. And the idea is relatively simple. If you have a configuration of matter and you let it undergo dynamically under gravity, two things can happen. It can either collapse into a black hole or it can disperse to infinity if you're in a symptotically flat space. Those are the two options. If you're sitting right in the middle, at the critical point, you will barely form a black hole. If you're a little bit under that limit, you will barely form a zero mass singularity. So Matchopwit in the 90s did a numerical simulation that constructed this kind of initial data and provided very convincing evidence that you can form a naked singularity by collapsing matter, fine-tuning the initial conditions. So this is a counterexample that you can construct in 4 dimensions. So in that sense, it sort of you could think that this could happen in our universe, but it requires really high fine-tuning. So astrophysically, doesn't seem very realistic.
The order parameter here is density constant, I suppose.
Basically, yeah.
If you have a magnetic field or something else, could you evade that?
I guess you have to fine-tune the magnetic field in order to do it. So I don't know if people have studied this in the presence of a magnetic field, but yeah, in principle, everything needs to be finely tuned such that you arrive at that critical point. Yes. So in the case of death by fragmentation, this is a huge family of counterexamples. And what they all have in common is that they constitute the endpoint of the Gregory-Laflamme instability. So you have an elongated horizon, call it a black string, call it an ultra-spinning black hole, etc. If you let it do its thing, it will tend to pinch off the horizon. So this is the second family, and this is what we'll.
Sorry,
yes.
Are we still in 4D, or are we already in higher dimensions here?
A little bit of both. So you can do this in 3+1 and higher, but here we only know these counterexamples in 5 and above. Yeah, there's no Gregory-Laflamme in 4D, to the best of my knowledge. So we're not going to talk about critical collapse anymore. We will concentrate on the second. And as I mentioned before, this is basically what we see in fluids. So very thin tubes of fluid undergo this modulation that ultimately leads to the pinching up of the horizon. So this is the physical picture that we can use as an analogy to think about this death by fragmentation. So yes, let's talk about this in a little bit more detail. As I mentioned before, this follows from the Gregory-Laflamme instability, and it was studied in detail in a full numerical simulation by Lenny Rabertorius in year 2010. So what is the basic idea? You start with an unstable black string in 5 dimensions, like here. So this is unstable. You perturb it a little bit, and you let it evolve by of course, the Einstein's equations in fact. So this is what will happen. You'll see that some ripples are going to form, and these ripples become stronger and stronger. So you have these beads here. So the string that connects these beads itself is unstable, and you form smaller and smaller beads. And in principle, this can continue forever, at least classically. There's no scales in GR, so you expect an infinite number of these generations to take place.
So yes. This bead in the center does it also have mass, and how much mass does it take from the total?
Exactly. Yeah, this is something that you can measure. You can look at the geometry. This something that is really important. I'll say a little more about that later. Is that these are, if you look at the geometry of this, these are black holes. Basically, these are Schwarzschild, higher dimensional generalization of Schwarzschild black holes, and the configurations in the middle are strings. So you can really think of this as a bead, as a necklace, if you want, where the beads are black holes and the thing connecting them are actual strings. Yes.
The area theorem is satisfied all the time?
Yes.
The singularity is the string?
The singularity will occur at in finite time, where when the radius of this of some of these bits goes to zero. Of the tooth goes to zero. Yes, that's very important. For a long time, people were very confused and they thought that this would happen in infinite time. And well, what's the point? You have to wait for an infinite amount of time. But yeah, this happens in finite time. So the width of this goes to zero in finite.
So you start with an unstable string. Does mean, I mean, all black strings are unstable, or this is?
No, only thin black strings are unstable.
Only thin black. What does thin mean? Like, there are two kinds of.
Well, there's a parameter. So when you have a black hole, for example, there's the radius of the horizon, right? And you have large black holes, small black holes. The strings is the same thing. There's the thickness of the string, and you can vary that. You can
below some thickness.
That's right.
And then the other question is this number. The color scale is what?
The color scale is some curvature invariant, but you don't have to worry too much about that for now.
I don't, because it seems to be larger, so if I would expect it to diverge with the string.
Yeah, sorry. Yeah, I stole the video, and I should have deleted this. I don't
so
have.
That's not the.
No, yeah. Forget about this color coding for now. What I can tell you is that curvatures are becoming larger and larger near the thinner parts of the string.
Because this is my other point. In principle, should I trust the simulation?
There's lots of numerical issues that you can have here in terms of resolution.
In the sense that if the curvature is not
sure.
trust the simulation, but trust the field. Where should I stop?
Of course. Yes, that's another way of thinking about it, that eventually, if this undergoes this an infinite number of cascades in finite time, you will, no matter what, reach a point where curvatures become transient. And maybe that's a better way to think about the conjecture, that classical gravity by itself will take you to a quantum regime. Maybe that's a nicer, sort of more physical or less mathematical, but more intuitive way of thinking about the weak cosmic censorship, that you can achieve Planckian curvatures in finite time. Yeah, thanks. What? Yeah. So yes, that's a very good question. So the claim in their paper is something that we're revisiting now, is that the first generation, the first formation, strongly depends on the initial condition. So how do you do this? After that, what they claim is that the self-similarity cascade is independent of all the other details, and they conjecture it to be universal. We're revisiting that, something that is being actively researched. So you can see here that it looks like this is preserving a C2 symmetry, right? But the beats don't. So there's something a bit off here.
So technical question, how long does it take to make this animation?
Well, this was 10 years ago and computers were a lot slower, but we're repeating this simulation now, and I can tell you exactly how long it took us for the case of the black holes. Is essentially 2 million hours in a supercomputer. Of course, in parallel, right? Yeah. Yeah, I wouldn't be telling this story if it took. Yes. Are you happy? No. Okay. So this is the full simulation, and the mechanism behind all of this is this Gregory-Laflamme instability that creates these ripples on the horizon of the black string. And ultimately, this leads to the pinching off, and this is associated to a violation of the cosmic censorship conjecture. So after this, other people, Paul Figueras and many collaborators have been working on other examples involving black rings and other configurations like ultra spinning black holes. And basically, you always see the same thing. So you start here with this black ring, it gets distorted, and locally it looks like the same thing that happens to the string. Also with ultra spinning black holes, here you also have a separation of scale because these are very pancake-like. So they start becoming more and more pancake-like until you end up with something that resembles more or less what you see in the case of the string. In this case, these are known to occur in 5D and above. For the ultra spinning black holes, people have found this in 6D and above. And the mechanism is always the same thing. You have some configuration that is Gregory-Laflamme unstable. If you let it evolve, eventually it leads to the pinching off of the horizon. So this is the general picture that has emerged after all this work. Okay, so usually people ask like, well, what is getting singular here? So that's more or less what Daniel was asking as well. So what do you mean by a naked singularity? Let's talk about that a little bit more. So this is a schematic depiction of the whole situation. So we start with an unstable string that is homogeneous. Because it's unstable, we see an intermediate configuration that has these ripples. These ripples are becoming sharper and sharper. So you have a configuration that looks more or less like this, where you have some big beads joined by strings to smaller beads. If you zoom in very close to the big blobs, that's usually where this thing tends to break first. At some point, this will reach zero radius. And in analogy to what happens to fluids, you expect here some quantum dynamics to take place and evaporate this little bead of string. And there's a change of topology. So this topology change is well known to be associated to the appearance of a zero mass singularity. So this is a little bit more precisely why this is a naked singularity. Another way to understand this is to notice that the curvatures are becoming higher and higher. So that at some point, like in this evaporation point here, classical gravity is not enough, and you need some quantum modification of it to tell you what to do. In the case of fluids, it's actually there's an analytic solution that allows you to go from this point to this point. So there's an attractor, and that is a really interesting thing that people discovered in the late 90s. Because when you have these numerical simulations, you're always worried that, oh, maybe if I continue evolving, something will happen and it will break this. I cannot fully trust this simulation. But in the case of fluids, you have an analytical solution that pinches off, that allows you to continue from the evolution to this point to this point. And because of that, you really, well, also you have an experiment in that case. And we understand this configuration really well in the case of fluids. In the case of gravity, we're trying to understand this, if there's this attractor a little bit better. That also leads to universal properties of this configuration. So in the case of hydro, it's there. In the case of gravity, it's not there, but we expect it to be more or less the same. Yeah, I don't think you can calculate the critical exponent. The width versus time is t minus t0 to a certain exponent. You can do that, but I don't think the precise location of it is something you can nail down with this theory of attractors. I haven't tried it myself. I mean, the simulations are already expensive enough. Where what I show you about black holes, we're now going back to the case of string. 10 years later of the first simulations, computers are more powerful now, and we're trying to understand precisely those kinds of questions as we speak. Then you had a question.
Between 5 and 6, nothing diverges.
When
you're running curvature is always fine.
Here, yeah, well, curvature achieves the maximum here, I would say.
But it's a finite maximum.
No, I think it would diverge. Yeah. Yeah, in the case of fluids, for example, the whatever equivalent of curvature, there's a true pinching off. The derivatives become singular.
And how does the simulation not explode?
No, it does.
But somewhere you get to 6. So you do like
This is not a simulation. This is a cartoon.
But the video you showed before is not the same.
And the video, no, the video doesn't pinch off. I will show you a video where it looks like it pinches off, but I'm cheating. I'll tell you when I'm cheating. I'll let you know. But in the simulation, you cannot do this. So especially if you expect it to be a fractal, you need infinite resolution to resolve a fractal. You cannot do that. So you have to stop at some point and then extrapolate what you think you've learned and hope for the best. And again, in the case of the fluid, you have an analytic solution that describes this pinching, and then you truly believe it because those are your same equations. But in the case of gravity, we don't have this. Thanks. Okay, so hopefully that whenever you have an elongated horizon, you can make it pinch off by the Gregory-Laflamme stability. But now the question is, how do you form this long horizon from the collision of two black holes? So I mentioned in 4D, we've done an immense number of simulations and we never see this happening. So we need the number of dimensions to be high enough. This is the upshot of this, the spoiler alert. So yeah, in 4D, this doesn't happen. We know that black holes are very, very stable enough that we can take photographs of them, so they stay put. And moreover, waves, gravitational waves in 4D tend to circularize everything. You radiate a lot of angular momentum in the case of 4D. So things are like to stay circular. You wouldn't expect these waves to allow this elongated thing. That's something that would radiate a lot of angular momentum that will work against the Gregory-Laflamme instability. And ultimately, you can think that these two properties are related to the fact that the gravitational potential goes like 1/r. It's long range, but it's sufficiently strong that things are not super flat. This is not the case in higher dimensions, where the gravitational potential goes like 1/r to the d-3. So this starts becoming faster and faster. So then we know that black holes are not stable in higher dimensions, and waves are highly suppressed in higher dimensions, also because of this property. But we do know, thanks to an effective theory, that this happens in an infinite number of dimensions. This sounds like a little bit funny, but it's a limit that is well controlled and well understood. This is a paper that we wrote with Roberto Ampara, David Licht, and Raymond Luna in 2018, based on an effective theory and the large limit that Roberto and collaborators have developed previously. So yeah, there's this effective theory. You take a black brane and an arbitrary number of dimensions. That black brane is described by its mass density and momentum density. You write down the equations, keeping d as a real number, the number of dimensions a real number, and you can rescale things carefully and take the limit where d goes to infinity. And that allows you to simplify your equations a lot. Of course, you need to be careful on how you take this limit, but it's something that Roberto and collaborators learned how to do many years ago. And you end up with an effective theory for these two variables. It's basically hydro for the mass density and the momentum density. So what this effective theory describes, it's a black brane with an infinite number of transfer dimensions. You get to keep some dimensions along the string. In this case, I'm keeping 2. And there are these lumps of energy and momentum that move around. And this effective theory shows you how they move around by solving this very simple equations that I'm not writing down here. So a little bit as a joke, when we were working on this, we always called this blobs, and we started calling this blobology, because it's a theory that describes how blobs work. And if you Google blobology, something that biologists do when microscopes started becoming more powerful, instead of just seeing just a fuzzy thing, they started to see blobs. And, well, it was like a little bit of a joke using the word that biologists had coined before us, but obviously it has nothing to do with it. So, and let me tell you just a tiny bit more about this blobology and why these lumps of energy are interesting to us. So it turns out that these blobs represent, in a way that you can make very precise, they represent black holes. So we have this effective theory, and we can find analytic solutions to it. Some of them describe black holes, and some of them describe black bars. So this is an analytic solution. This is a Gaussian profile of the mass and accompanied by some Gaussian profile of the momentum that solve the effective theory. And well, this is a stationary solution. And if you look at the properties of this solution in the effective theory, you can convince yourself that this is basically a Myers-Berry black hole. So you're just looking at the geometry. Remember that this came from taking the limit in the geometry. If you study the limit carefully, this is basically the cap of a black hole, the north pole of a black hole. Yes? Right. So this is just the north pole of the black hole. So the horizon is basically extended along this whole thing.
So this is all inside a brain, which is what collimation.
Right. So you have a brain that has a blob.
Brain that is collimation 1 or?
It's dimension 2 in this case.
Okay. And then you study perturbations.
You can do all sorts of things. So the first thing you can do is to find an analytic solution of the effective theory, and it's just this Gaussian profile. And if you go back to the original theory and look what are the consequences of having that configuration, you can see that this is the zoom in the north pole of a black hole. And as you say, if you study within the effective theory the quasi-normal modes of these guys, it gives you basically a really good approximation of the quasi-normal modes of the full black holes in the spherical case. So that gives you some confidence that these configurations, you can think of them as black holes in higher dimension. One of the instabilities of these black holes are dipole instabilities, and you can study them. Moreover, you can construct nonlinear solutions that allow you to extend these dipole deformations, and these are the black bars. These are also analytic solutions of this theory. It's basically an oblate Gaussian that is rotating. So yeah, it's very surprising that you can find an analytic solution for this, but you can. And yeah, these black bars are basically just dipole deformations of these black holes. And in 6 dimensions and above, black holes are known to contain these instabilities. Yes.
So if two of these blobs collide, like two black holes in our universe,
yeah,
when they merge, they will end up being one big object, just like black holes.
Yeah, that's the next slide.
Quasi-normal modes, can you differentiate them easily from those that we observe here in 4 dimensions? Or could you argue that we are seeing the 4-dimensional projection of such a space?
Yeah, the effective theory only captures a subsector of quasi-normal modes. And in this case, the quasi-normal modes that you capture are precisely the ones that are unstable. So in our universe, we don't have those, and it's quite clear already that at this level, this is not something you can easily connect to astrophysics. No. Moreover, because of the way we're taking the limit, gravitational radiation is a non-perturbative effect. You cannot see any effect of radiation. So mass and angular momentum are strictly conserved in this series. That's and also an important difference. Okay, so as Juan was saying, if you have something that you start feeling more comfortable with calling a black hole, and you can put 2 of them together, it's almost impossible to resist the temptation to make them collide. So this is what we're doing here, and in this simulation, and the effective theory takes, I don't know, a minute or something in my old laptop. So it's really something easy to do. So you have these two black blobs, and we're going to set them in collision course, and they will merge. And if the impact parameter is sufficiently high, they will form a black bar. If the collision is head-on, they will just form another blob, and nothing too interesting will happen. But if the impact parameter is sufficiently high, they will form a bar. And in some cases, this bar can be unstable itself to Gregory-Laflamme. So this is what's going to happen here. So they merge, they form a bar. Bar is more or less metastable. It takes some time to decay. But because of Gregory-Laflamme, it ends up splitting. And Daniel, this is maybe tricking you into thinking that you can continue the evolution past pinching off, but this is not true because there's never a pinch off here. The only lessons that we're trying to extract from the simulation is that you can take two blobs can form a bar, and if the angular momentum is large enough, this bar will be unstable. So this is the lesson we're extracting from the effective theory. I wouldn't do I wouldn't trust any details past this point. So yeah, this is the summary. So if the angular momentum is sufficiently long, the collisions form unstable bars. And in a sufficiently large number of dimensions, radiation is very, very suppressed. And Gregory-Laflamme will always win against radiation. This is your competitor to outdo, right? And if D is infinity, there's no radiation and Gregory-Laflamme always wins. So then we have this prediction that for D equals infinity, we will see this effect. And the interesting question here is, well, how big you need D to be for this effect to actually happen? It's a bit disappointing to say that, well, if D is sufficiently large, this will happen. You want to know more or less when. So here's the intuition of how we started thinking about running a simulation in finite D. So these simulations are really expensive, so you better have a good intuition for which corner of parameter space to explore. So let me give you some intuition of the kind of criteria that we were after. In high dimensions, also because the potential decays as 1/r squared and higher, there's no in spiral. So in 4D we have in spiral because the angular momentum barrier and the potential have the same power. So one is one over r squared and the other one's 1/r. So we have in spiral because of that. In higher dimension, that's no longer the case. So if the impact parameter is too large, the black holes will just affect each other. They will not merge even. So that's boring. That's not something that we're interested in, at least for now. If the impact parameter is too small, you will just form a central black hole. And because there's some angular momentum here, some orbital angular momentum, this final black hole will have some spin, but it will be a black hole. Also not interesting for our purposes. But in some case where there's enough orbital angular momentum and perhaps some spin, you can give this black hole some spin, you expect this bar to form. And if this bar is sufficiently elongated, it will decay via Gregory-Laflamme. So this is what we're after. So yeah, we need to first of all form a horizon. And for that, the impact parameter cannot be too large. We also need sufficiently large angular momentum. So we need B, the impact parameter, to be not too small. Also, if we add spin, it's also a good feature for us. And our enemy here is radiation. So how do you suppress radiation? Well, taking D to be sufficiently large, and you can keep the velocities of the colliding black holes to be small, because it was known by some previous numerical simulations that if the velocities are large, then you radiate more. So you want to keep the velocities to be sufficiently small.
Anti-aligned spins, do they do the same no spin at all?
Yes. Yeah. Yeah. If here the spins are anti-aligned, you will end up in a situation like this. Yeah. By mistake in my code, I thought I was aligning the spins. I was anti-aligning them, and I wasn't seeing it. And we also would like to understand this picture better. So there better be some bar modes that would describe this sort of configuration. And these bar modes are known to occur in dimension 6 and above. So we start looking in this minimum number of dimensions first.
So with the number of dimensions is phenomenology, or you really can say, no, they only occur in D bigger than 6, or you know that because simulations haven't found them in D equal 5.
So you can study black holes in arbitrary number of dimensions, and D equals 6, you find instabilities. and d equals 5. 5 is a marginal case. Maybe we can talk about it at the end. And 5, there are no bar modes. So yeah, there's
There are no, it really means, because sometimes knowing if there's an instability is not like a.
Sure. Yeah, absolutely. People have worked a lot and they have found instabilities of this kind and 6 and above. Yeah, showing that something is stable is a lot more complicated than showing that something is unstable. Yeah, I fully agree. So yeah, we're just, trying to write a proposal, and in that proposal they ask you what parameters you want to explore, and you have to give some intuition. Yeah, this is what we. Okay, so finally we arrive at this topic of the collisions in finite. Okay, so what is the problem that we need to solve? We're solving Einstein's equations in vacuum. Really easy equations to write down, not so much to solve. And the initial condition is 2 black holes that are in collision, of course, with some impact parameter and some aligned spins. This is the problem. And well, easier said than done. This takes a lot of effort to solve in a computer. So there's lots of things that happen. So you have to choose a gauge, you have to implement your numerics in a code, you have to, of course, then parallelize it. In our case, we also have to implement the dimensional reduction, because typically these codes are 3+1, and you also need to take care of that. But luckily for me, I started late enough that this was already more or less implemented in this open source code called GRTOM. So there's not a lot to worry about. What we had to implement from scratch was the initial condition, but that was the easiest part. Everything else was already taken care of. So we did 3 detailed runs. We did a few cheap runs to try to find good scenarios, but it didn't take a lot of effort. So there was no fine tuning involved. We did a couple of cheap runs, and we already saw a bar that was starting to elongate, and we took those candidates and continued the production runs in this case. So we did 1 detailed run in 70 and 2 detailed runs in 60. And after 5 million hours of computations, we made some pretty pictures that we could show our friends.
Is it easier or more complicated to draw initial conditions in more than 3+1 dimensions?
Yes, it's easier in the following sense. So because of the gravitational potential decays a lot faster, you can basically just superpose 2 black hole solutions. And if they're far away, the constraint violation will be small, simply because their interaction is heavily suppressed. So in that sense, it's a lot easier. We didn't do anything sophisticated like to puncture initial condition. That wasn't really necessary. We just took our favorite, it's what's it called, Kerr-Schild way of writing down the moving black hole. And then you just superimpose those 2, and the constraint violation is pretty much fine if the separation is reasonable. So in that case, it's a lot easier. Right, so now that we know a little bit more of how the sausage is made, I can show you the simulation again, and we can appreciate a little bit better what's happening. Yeah. This, well, yeah, I have to tell you what's the color coding. So I'm showing the conformal factor. That is one of the variables that you evolve. Yeah, I don't know exactly what this means. So these are boosted, and it might be related to the fact that these are boosted black holes. But yeah, I'm not sure. So instead of decaying to a black hole, this continue to go their own ways and form this beautiful fractal pattern in the middle. Yeah. Okay, so what are we monitoring here? Sorry, I have to. Good. Sorry, this slide is a little bit busy, but okay, we want to understand that there's a singularity forming, so we better track the horizon. In dynamical settings, the best or the closest thing to an event horizon you can look at is the apparent horizon. And in this case, it's even really hard to technically find this. You have to solve a partial differential equation with a very complicated contour. So what we did was to based on our previous result from these people that did it in a case where I think this was for a black string and other more symmetric circumstances. They actually found the apparent horizon, and they experimentally, phenomenologically noted that some contours of the conformal factor allow you to track the apparent horizon. This is an important technical result for us. So it was very useful to start just simply plotting the conformal factor in this color coding, and I'm guiding your eye by drawing this extra contour here, but this is an important technical point. So instead of tracking the full apparent horizon, that is technically pretty much impossible in our case, we're tracking the conformal factor. Yes, so you do an ADM decomposition, right? A 3+1 decomposition. And then you end up with the spatial metric and the extrinsic curvature. Right? And then depending on the implementation, you can write down your the spatial metric as a conformal factor times a metric that has determinant 1 as part of the technical implementation. The conformal factor is this guy here. Yeah, thank you.
And when it's 1/2 is where the horizon is. When did you write 0.5?
Here I'm plotting 0.5. This
so
is
the 9 is where the common factor takes the value 0.5.
Yes, and
Is this for a reason?
It's a dimensional dependent thing, and this is I think I made this plot in 6 dimensions. It turns out to be the case that in this paper they show that depending on the dimension, contours of constant chi coincide with the apparent horizon.
Of any constant chi or?
It depends. In this case, it's 0.5, but in higher dimensions, it can be different.
So how do you know of the value what is correct value and the price?
Right, this is this slide. Sorry, this is also a busy slide, but it's yeah, we stole this trick from linear amplitudes. So we're trying to understand what is the approximate geometry of our horizon, and the upshot is that these are black holes that are connected by strings. So how do we know that? Of course, looking at the full metric is very complicated. So what linear amplitudes did, and something we're mimicking here, is to compute some curvature scalars. So the first non-trivial curvature scalar you can compute is the Gravitational scalar, right? So because we are in vacuum, r mu nu would be 0, right? So the first non-trivial thing you can construct is this. It's the Riemann curvature square. Because of dimensional reasons, you have to rescale it by the width to the 4th. So what am I plotting? Here, when I say horizon, I really mean some contour of chi of some value that I will adjust. And I'm also plotting this. The contours where k corresponds to a black string. That's in white. So I can convince myself that they are very close to each other if I choose the value of chi properly. This is a bit convoluted. I don't know if I'm able to explain it.
Wait, the white is the k, and then what is the chi? The red.
The black is the k. That's the horizon.
And black is k.
Yes. Sorry, no. White is k. Good. Black is horizon. Chi and k. Yeah, sorry. Conformal factor is black. So I choose a value of chi, 0.3, I think it's in this case. And I notice experimentally that this value of the conformal factor coincides very well with what I expect there to be if this were a black string of that width. If I do the same exercise, now computing this value for a black hole of this size, I get a different value of chi. But you can see that they more or less follow each other. This is just this tiny one. So this provides extra evidence that the geometry of the horizon is that of a bunch of little black holes joined by black strings, simply because the values of the Stretchman scalar coincide on the given surfaces. This is something that Lehner and Pretorius also did to track the geometry of the horizon. Good. So we also extracted gravitational waves because this was our main enemy. So if gravitational waves were not suppressed, we wouldn't see this. So we wanted to get an estimate of what they look like. And we get something like this. The absolute values are not very important, but you see that there are two peaks. This is something that was originally a bit surprising to us. So this is merger. And this large peak here is not merger. So we were a bit puzzled by that, because in 4D, the highest peak is merger, and then you don't get anything else after that. It's just ring down. So here, you start with the black holes with some certain separation. Yeah, there's an offset here, but this t equals 0 corresponds to this point here, to this first merger. Then around this point, where the black holes start to spread, where the tensor of inertia is becoming more and more elongated, you get this extra peak. It was a bit surprising to us. But then after that, you don't get a lot more. So the total amount of radiation that you emit is very, very small compared to the original energy of the black holes.
So when you're saying the second peak, talking about the huge one? Or
Yes, this one.
Okay.
Yeah, this. Yeah, I don't really know what this guy is, but this is merger, and this is this point here.
From the absence of such a measurement in LIGO, could you infer what's the constraint on the existence of?
Yeah, in principle, but I think we have many other good arguments to restrict it. So you probably don't. You don't need to work super hard to rule this out.
It does depend on the size of the data, right?
Right. Yes.
So this dimensions 8, 5, and 6 identical to the other.
Yeah, we only extracted this in one of our simulations. Yeah, we didn't have the waves for all of them. Yeah. Actually, that's a good question. We don't know how this depends on dimensions.
But the dimensions are not from.
No. Sorry. Yes. No, they're not compatible. Yeah. Yes. So, well, the upshot of this exercise is that we confirmed the hypothesis that radiation is very small, and the angular momentum that you also radiate will never be able to stop this cascade simply because it's tiny. Okay, so we're coming to the end. What are the main conclusions we can extract from this work? Is that, well, of course, first of all, there's a new evidence for violation of the weak cosmic censorship conjecture that involves collision of black holes in higher dimensions. That is the main one. Also, it was interesting to see that we can trust to a large degree what this D equals infinity effective theory is telling us. So it was useful to use this theory. Yeah, that's pretty much it. The picture that I like to keep in mind is this one of the fluid breaking up. And the main open question that we're looking into at this moment is that are these two paradigms really the same? Is gravity behaving like fluids? And more concretely, what we're trying to study is in more detail this moment of pinching off. Is there an attractor in particular that describes how the horizon is breaking up? And that would imply that there's some universality, some high degree of universality in this process. So thank you so much. Are there any more questions? Yes.
And so this is obviously a very interesting academic exercise. But so what do we learn about the real world?
Yes. What do we learn about the real world? Well, maybe you can just repeat what I said before, that if we try to understand the counterexamples to the conjecture, we can try to reformulate it in a way that more precisely can hold us there.
So here the message is that this doesn't happen in 4D because we radiate too much.
Yes.
The angular momentum.
Correct. That's what I would say. Yeah.
But this is so. The question could be, so to which level of generality would have that? Because this is an example where we have collisions of black holes. So okay, we know that when we have a collision of black holes in 4D, this doesn't happen. I mean, pinching of horizons doesn't happen. But I mean, I suppose that black hole collisions is not the only situation that we might expect, where we might expect violations
right.
That of the censorship principle and conjecture in general.
Yes, yes. People have tried, for example, to overspin black holes. So you have a spinning black hole that is very close to extremality, and you throw another particle that would make it spin a little bit more. And if you do a simplified calculation, for example, some probe limit, you get that you can violate the conjecture. But the moment you start taking into account back reaction and radiation and things like that, you see that the theory protects itself. There's a censor, so that protects the censorship. So it's more or less along those lines.
So did you simulate always in 6 or above?
We did some 5D simulations, trying to look for counterexamples in this marginal case, and we couldn't find any.
In what way is it marginal? What things happen and what things don't happen?
Right. So I call it marginal from a Newtonian perspective, that the gravitational potential and the angular momentum barrier are both 1/r². So, for example, that has the implication that you can find bound orbits if you fine tune. For example, that's something marginal. If you go to higher dimensions, you cannot do it. But in 5, it's more or less like these two are competing on equal ground, so you can construct some trajectories that are bound, but only if you find tune. Also, what doesn't happen is that there are no linear instabilities for black holes in 5D.
There are no linear instabilities for black holes.
Yes.
Which there are in 6.
Yes. So if this were to happen in 5D.
So, but if you manufacture any type of elongated thing, you will Gregory-Laflamme pinch. No?
Probably, if it looks a lot like a string, then
let's say I put 100 black holes one after the other in a line.
Sure.
They are close, and I let them go. They will merge, they will follow each other, but they will pinch before they construct a big one, just by accumulation.
Based on the results for the black string, I would presumably think that would be the case. But coming up with a good initial condition that does it, it's not super easy.
So is it more difficult to simulate in 5 than 6?
No. It's more difficult with a collision of black holes to achieve this sort of thing. That's what's more difficult. But doing the simulation in 5D and 6D equally hard or easy.
So what you talk must show that they are in any number of dimensions. But do you have any intuition what would happen in modified gravity?
Well, those are hard to even mathematically formulate in terms of the initial value problem and things like that. So yeah, I know that people have tried, some of my collaborators in particular, but yeah, I don't really have a lot of intuition. I know it's a lot fun.
When each pinching produces singularity, so when one horizon surface becomes true, there is a singularity, but why is there no singularity when, for example, 2 black holes merge and come to surfaces with one, which is like time reverse?
Yeah. I've asked myself that question many times. I don't know the answer. I'm sure there's a good answer for it, but yeah, right this second, I don't know what the answer is. Yeah, somehow it's not really reversible. I mean, what gives you the notion of reversibility is, or irreversibility is the fact that entropy is always growing. So here entropy is always growing. So you have second law of thermodynamics. So based on that, I would say that it's not just simply reversing one into the other. But yeah, why don't you have a singularity when the horizons fuse? I think it's a really good question, and I don't have a clean answer at this moment. But thanks. Mm-hmm.
You sum up the two areas.
Yes.
So if you split them up, then you divide them. Unless the surface that you form is never going to two areas.
It's tiny. So yeah, the original argument that Gregory and Laflamme gave is that if you compare the entropy of a string and the entropy of a collection of black holes, then the collection of black holes has higher entropy. So that configuration is favored thermodynamically. So that makes you expect that would be the endpoint of the instability. Sorry?
There is a
yeah. Yeah. Well, thank you so much.
The chairman should end
Sorry. There's been a lot of questions. Any more questions? Okay, then let's thank Tomas.
Thank you.
I don't know if there's people in Zoom. They already left.
Okay.
So I have another question.
Yes.
Of